All right, it is a couple minutes past the hour, so I think we'll go ahead and get started. So hopefully everybody here is intending to sit in on a webinar for reverse engineering. That's what we'll be talking about today. All right, so a little bit of an overview of our agenda for this morning. I've got a quick PowerPoint, a few slides as an overview of this subject, and then what we'll be doing is a live demonstration of Geomagic Design X to go over some manual surfacing, automatic surfacing, and parametric solid modeling. And then we'll do a quick review of a pre-existing hybrid solid modeling project. Also, if anybody has any questions that pop up during the presentation, if you could go ahead and put those in the chat, and I will be checking that periodically to make sure we get those answered before we wrap up for this morning. All right, so before we go crazy here, we'll talk a little bit about Neometrics. So we are a engineering service provider as well as a reseller of 3D equipment such as 3D scanners and 3D printers. We're authorized resellers for companies like Creaform, Markforged, BigRep, Geomagic, and others. So talking a little bit about scanning, right? There are lots of different types of scanners available. So I like to say scanners are like screwdrivers because there's really no one tool that does everything. So you've got tools available like articulating arms here with a laser scanner attachment. We've got some handheld solutions here from Creaform, as well as tripod mounted systems from other manufacturers. Those would be available both as like short range units like this EVIC scan for smaller parts that would be scanned on a turntable, or something like this ZNF scanner here, which is a long range system, which is great for doing big things like buildings and airplanes and boats and things of that nature. So there's really not one scanner available that'll do everything from, let's say, nuts, bolts, and screws all the way up to entire buildings. So depending on what your application needs are, it may require more than one type of scanning tool to accomplish that. So what are applications for 3D scanning? Scanners basically collect, data points. And once we have those data points, there's sort of two paths we can follow. One is inspection, where you compare your scan data back to your original CAD model. And the other is reverse engineering, where we create the CAD model from the scan data. So today, of course, we'll be talking about the top path here, which is reverse engineering. So in my world, when I say reverse engineering, I'm talking about creating 3D CAD models from scan data. Before we go too much further, we've got some buzzwords and terms I'd like to quickly go over that you may experience in this world. So first is digitizing. This is kind of an older term that you hear, whereas you're capturing data points, typically with some kind of mechanical device, one point at a time, to capture the shape of an object and get that shape into a computer. 3D scanning is digitizing, but using an optical device, such as a laser scanner or a structured light scanner, where we collect millions of data points very, very quickly. So scanning is really, digitizing, but in a faster, more accurate method. Those two types of processes will typically create a point cloud or a cloud of points, where every measurement is stored as an XYZ data point. So of course, if you have millions of them, it looks like a cloud. So kind of the top image here in our slide is representative of what a cloud of points looks like. The next sort of geometry that evolves from the point cloud is a polygon model, where all the data points you've captured are then connected with tiny little triangles. So if we look at the image on the bottom of the screen, that is a polygon mesh, which we would typically save as an STL file. And those of you that are involved in 3D printing might be familiar with that format because most of the 3D printers available today operate using those STL files. And then finally, reverse engineering again is creating CAD models, real CAD, from either those polygon models or point clouds. So there's kind of two different types of 3D geometry when we're referring to a 3D CAD model. The first being a surface model, and that's going to be an infinitely thin skin. So it's not a solid object like a solid model, but it's just really, it's a skin, and it's not going to be fully closed. And you can create that either through manual methods, automatic methods like auto surfacing, or what I call rapid surfacing, which is kind of halfway in between auto and manual. And we'll go through a couple of those examples later on during the live demonstration. Next is a solid model. So a solid model is really just a surface model, but is fully closed. So unlike the top image here, which is open on the back and the bottom, a solid model is going to be a fully closed volume. Now, you can create a solid from some of these surfacing techniques, like auto surfacing, or you can create a parametric model where you're building the model feature by feature and sketch by sketch. Now, when you create a parametric model, that has a model history. So all of your steps in the process are recorded. A feature-based model is really very similar to a parametric model, but is not going to have that model history. So for example, if you create a parametric model and then save it as an IGES or a step file, you're going to lose that history. So you have the geometry, but you don't have the steps by which that geometry was created. And then finally, we have a hybrid model, and that's going to be something where maybe you've created the organic geometry through some of these auto or rapid surfacing methods, but you've got some mechanical features in there that were traditionally modeled. And again, we'll cover that in a little bit more detail later on. Okay, so choosing your modeling method. I like to refer to bricks and potatoes. So obviously a brick is very geometric. That's easy to create as a feature-based model, right? It's basically 6 planes trimmed up to give you that shape. Whereas something like a potato or a bone or something very organic would be very, very difficult to model using a traditional method, cutting a section, doing an extrude or something like that. So for those types of organic shapes, we would use an auto surfacing or rapid surfacing method. So here's a typical workflow where we have a small casting. It was scanned in 2 different positions. So we've got 2 different data sets here. We use alignment or registration to put those together and then merge them to create a single data set, typically a polygon mesh. Once we're at that stage, then we can clean that up by smoothing it, filling holes, sharpening edges, and maybe decimating it to reduce the file size. Now, if we're going to use a rapid surfacing technique, we need to make sure our polygon mesh here has no defects in it. So no holes, no non-manifold vertices or things of that nature. Because what we're going to do is then lay out a network of curves. Typically, those will create tiny, what we call patches, which are regions that are bounded on 4 sides by curves. Then those are used to create the surfaces. And so it's basically a shrink wrap onto the underlying scan data. And then if we do a 3D compare to compare our final results back to our STL file or our polygon mesh, we'll see the results are typically very, very accurate. So that's one of the benefits of this method is you get a very, very accurate CAD model, even for a very organic shape. Now, for more geometric or mechanical parts, we would use parametric or feature-based modeling. So in this workflow, this is a small turbine blade here. You can see the scan data, the STL file, has got some different colors to it. It's been separated into different regions, which can be used to create geometry. Typically, what we'll do is we'll cut cross sections and then develop 2D sketches. And then from those sketches, we use traditional CAD modeling techniques like extrude, loft, sweep, and revolve to create our solid bodies. Once that solid body is done, then we would usually send that over to the native CAD system. DesignX has the ability to do what's called a live transfer, where that model, the model history here, is transferred step by step into these native CAD formats. So that would yield a parametric CAD model in the native system. If we just exported our final model as a step file and then imported it into the final CAD, then that would be a feature-based model. So hybrid solid modeling uses techniques from both workflows. So geometric features would be modeled in a parametric method. The organic features would be modeled using rapid or auto surfacing techniques. And those are typically used, or we use them here on, let's say, injection molded plastic parts where you have an exterior housing, which is very complex. So we'll rapid surface that, and then we'll go back in and add in all the ribs and bosses and those types of features using a parametric model. Now, there are lots of different types of reverse engineering software tools available on the market today. Today, of course, we're going to be talking about Geomagic Design X. That's kind of our flagship product and the flagship product from Geomagic for this type of workflow. Also available from Geomagic is Wrap, which is a polygon editing tool, as well as a rapid surfacing tool. No parametric or feature-based modeling available there. However, if all you're working on is organic or art, sculpture, things of that nature, then Wrap might be a very good choice for you. For SolidWorks users, there's Geomagic for SolidWorks, which is has a series of tools that operate within the SolidWorks environment, similar to DesignX, but not quite as featured. And then, of course, Creaform has their own VX model package, which runs in the VX element environment. Again, it's not a 100% solution. It's designed to extract CAD features and sketches and then send them over to CAD programs like SolidWorks. And then there's a few other products there, of course, available on the market. But today we'll be going through DesignX. Again, a flagship product here. So it has a full suite of tools to take you from point clouds to STL files, rapid surfacing in parametric solid modeling, all in one environment. So looks like we don't have any questions that have come through yet. So I'm going to go ahead and tab on over to DesignX. So for our first demonstration, what we'll be doing is working on an organic part. I had stolen some of my wife's Halloween decorations here. So we have a plastic skull that we scanned. So this was scanned with Creaform Handy Scan Black. So as you can see, it was done in two different pieces. So much like in the PowerPoint, first thing we're going to do is align those together. So in our alignment tab, we're going to go align between scans. And we're going to do local based on pick point. So here we pick a reference object and a moving object, and those appear on the right window here. So I'm going to rotate this one around, and what we need to do at this point is find areas of commonality between the two data sets. So if we look at a profile here, we can pick on the cheekbone here and upper part of the skull and do the same in the lower image. And then we can see on the left side of the screen, we've got kind of a preliminary alignment based on those pick points. Once we hit this checkbox, then the system's going to do a best fit between those two. Okay, so our two meshes, our two STL files, are now aligned together. Next step would be to merge them to create one data set. So we're going to go to our Polygon tab, and we're going to go merge. We've got several different merging options. It's really a matter of a trial and error depending on what type of scanner you're using and the data you're starting with as to which one of these is going to work best for you. Since I rehearsed this yesterday, I decided to go with the HD mesh construction. That kind of gave us our best results. So I'm going to hit the checkbox there, and after I do that, now the system is combining those two data sets, but what it's also doing is it's retriangulating that data in the areas of overlap. So we get a nice clean mesh when we're done. Okay, so now we have our merged data set. Now, I didn't do the best job scanning, admittedly, so we have a few holes. And as I mentioned in the PowerPoint, we're going to need to address those before we move on to doing any kind of surfacing. So again, we're in the Polygon tab, so I'm going to go to Fill Holes. So I can pick the boundary of a hole and then hit OK and fill these one at a time. Or if I do a window and drag my cursor over the entire object, we can see all of the holes are highlighted. And we're going to hit the check. And now there are no more holes in our mesh. And also, before we go too further, I'm going to check the size of our polygon mesh. So I've got 1 million polygons here. That's probably a little bit overkill for what we're doing today. And to save time in my follow-on processes, I'm going to go ahead and decimate that. And we're going to bump that down to 100,000 triangles. So decimating can be useful in keeping your file size down, but you don't want to decimate too far down because you may start to lose detail in the object that you scanned. Okay. So since this looks pretty much the same as it did before I decimated, I know we didn't go too crazy with that decimation, and now we're down to just under 100,000 polygons. So there's a couple different ways. If I want to create a CAD model, a real solid model from this STL file, a couple different ways we can do that. First, I'd like to demonstrate some manual surfacing. Now, it would be a little bit tedious to manually surface this whole object, so we're just going to do a small portion. So first thing I'm going to do is create some curves, and I'm going to do that by cutting some sections. And I can do that by drawing some lines on the screen, and those lines being perpendicular to the screen will give us a plane in space, and that gives me those 2 section curves there. All right, it's a little crooked. Let's undo that and let's draw those again. That looks a little better. Oh, now it's crooked the other way. Well, we're going to just roll with that. Okay, so if you recall from the presentation, what we want to do is create these patches, which are areas that are bounded by 4 curves. So I'm going to manually lay these patches out. A couple more to go. Okay, so I've kind of created this headband of curves, and we'll use those curves now to create some surfaces. So I'm going to choose the legacy boundary fit. This is an older function, kind of before the auto surfacing was available here. And now in between all of my curves, we're going to create individual little surfaces. Okay, so if I hide my scan data, now over in my tree, we can see I have a boundary fit surface object. So it's not a solid, it's an infinitely thin skin, so it's not fully closed, no mass properties or anything like that. Now we can also check our accuracy using our accuracy analyzer and get a color map. So right now we've got a tolerance here of 0.004 of an inch, so everything green is within 0.004. So we can see we get a few areas where the deviation is a little high. Now there's a couple different ways we could address that if we'd like it to be more accurate. I'm going to go ahead and double click on that boundary fit object in my tree. And here we can see when we first created these surfaces, we did it by the number of control points within each patch. I can then change that to allowable deviation. And let's say I'd like it to be accurate to 0.002 of an inch with a maximum of 50 control points. So that means that those surfaces now are going to stick more closely to the underlying scan data, but they may require more control points in each surface to do that. So it's going to be a more complex surface model, and the file size will be a little bit bigger. So now we hit our color map, and we can see the whole thing is green, so everything is within that 0.004. Also, if I bring my cursor over the surface, we can see, oh boy, these are really accurate. So down to like 1/10. So that's manual surfacing. So you could easily see if I wanted to surface the whole object that way, that would be quite tedious to ensure I get all 4-sided patches everywhere. So the other alternative is to do what's called auto surfacing. So it's under the exact surfacing tab. So we're just going to go ahead and hit the auto surface button. We get a couple different options here for mechanical objects or organic. So we're going to choose organic. And once I hit this next button, now the system is going to do that curve layout for me, ensuring that every little patch is bounded by 4 curves. And it's doing the whole object all at once. So although it takes a minute or two to calculate, it's doing a lot of work for you. So here we can see our curve network. If for some reason you wanted to edit this, you can grab these nodes and kind of pull and tug and move them around. In general, you probably won't have to do that. But we're going to go ahead and hit the checkbox now. And just like with the manual surfacing, within every little patch, it's going to create a surface and then knit all those surfaces together. And it should give us a solid because it is going to be a fully closed volume. Okay, so we're going to hide our scan data. And now we can see this is a fully closed volume. So it shows up in our tree here under solid bodies. And if we check the accuracy, we've got a pretty accurate model there. A couple of spots, it's a little out of our tolerance. We could address that by bumping up the accuracy slider in the auto surface tab. But for our purposes today, I think this is pretty good. Now, when working on organic objects like this, sometimes our customers are interested in creating a hollow version of this. Maybe they want to create some kind of housing or shell this out for some kind of production. One of the downsides of an auto surface object is you really can't use tools like a shell or a thicken. The geometry is just too complex for the system to handle that. So the way we address that is we're going to cheat a little bit and we're going to make a copy of this mesh. And then we're going to offset that to represent the inner wall of our shelled object. So if we go to our polygon tools again, we're going to go offset. And let's say I want to create an object with a 1/4 inch wall. We're going to hit the check there. And it's going to take all those polygons now and offset them to create that inner wall. So now we have a new mesh, which represents the inner wall of our shelled object. So I'm going to go ahead and go back to my exact surfacing, and we're going to auto surface this again to create the inside. And that's going to give us another solid object in our tree. Okay, so now we have a solid that represents the inside, and we have the solid that represents the outside. So we're going to do a Boolean operation to cut the inside from the outside. So you can't see right now. It is hollow though. So I'm going to go ahead and just to prove that, we're going to draw a plane on the screen, and then we'll cut it to show that we do have a hollow auto-surfaced body. So here we can see now we get the inside, we get the outside, and we've got a nice uniform thickness. So what we just went over here in that little session was aligning and merging 2 different sets of scan data, a little bit of manual surfacing, auto surfacing, and then creating a shelled or hollow object from an auto surfaced body. Before we go too much further, I see we had a couple of questions that came through. The first one is, what is HD? So I'm assuming that's in the merging. Let's go back to that command real quick. And I'm going to just pick 2 objects so we have something to work with. So if we go back to our polygon tab, oh, looks like I can't open that unless I have two meshes without child entities. So let me import those again to answer that question. Bear with me just a moment. Okay, so I've re-imported those two data sets. Now we can merge. Okay, so among the 4 different types of algorithms we have available in merging, we have the surface merge, volume merge, mesh construction, and HD mesh construction. The HD stands for high definition. So it's really a more advanced algorithm that's developed from the other ones. And quite frankly, I don't really know the mathematical differences between the 4. Like I said, depending on what scanner you're using, will sort of dictate which one of these methods works best for you. And we've discovered that for this application, the HD gave me the best results. So a little bit of trial and error there. There was another question here. Can this one scanner get real color? Okay, so I scanned this data with the Handy Scan Black. That is not a color scanner, but the Creaform Go Scan Spark is a color scanner. So not quite as accurate as the Handy Scan Black, but does have the additional ability to collect color. Okay, I think that's it for the questions right now. So I'm going to go ahead and jump on to the next portion of our demo, and that's where we're going to do some parametric modeling. Okay, so I have another data set that I scanned, also with the Handy Scan Black, because we had that set up yesterday. So this is the STL file we got from that. I've already cropped out some of the table that we had scanned the object on. So we just have a nice little clean data set there. So first thing I'm going to do, our parametric modeling workflow is do an auto segmentation. So again, if you refer back to the presentation with that turbine blade, this function analyzes the shape of our object and kind of separates it into the different features that make up that shape. So this is handy because you can take a region here and I can create a reference plane. And we'll see a little bit later on that we can also use those regions to create some CAD modeling features. Before I do that, I'd like to point out that my object here is not aligned to my coordinate system. So that's my first step. Well, I guess my second step, since first we did the region. So I now need to create some datums on this object so that we can align it. So I've got the plane of the table. That's going to be useful. Unfortunately, there's really not a lot of other straight lines on this object, but the part does appear to be symmetrical. So I'm going to create a plane of symmetry. Now that is a 2-step process where first I kind of give it a first guess by drawing a line on the screen. Then with my first guess and my scan data selected, I have the option to do a mirroring. So I've got 2 features now that I can use for my alignment. So we're going to go to the alignment tab and we'll do an interactive alignment. So my first plane will be the plane on the table. Next, I'm going to pick the vector. So if I pick the plane of symmetry, it'll intersect that base plane to give me a location of my x-axis. I'm going to just flip the normal there because I like my z to go up. Now at this point, I don't really care where the origin is, so I'm not going to put a specific position there. Okay. So now the alignment's done, so we can see we've got a nice orientation of our data to our top, front, and right planes. So that makes the whole modeling process easier because then we might be able to later on take advantage of things like symmetry and so on and so forth. Okay, so to begin modeling this part, I could manually use a plane and cut a cross section and do a sketch. But today I'd like to show you some of the wizards available. So we're going to use the extrusion wizard, and this is going to allow us to take advantage of those regions. So I'm going to pick the regions that make up the sides of the part. And I click top. I'm going to pick this top region here. And for bottom, I'm going to go ahead and pick my front plane. So what it's going to do in the background here for us, once I click that next button, is it's creating a sketch for me and giving a preview of that extrusion. Now, not only is it doing an extrusion, but it's also extruding up to a freeform surface that it fit on that top region. So I'm going to go ahead and hide that. So now we can see here's our first solid body. All right. So we've got this region here. So if we were going to do this model, this object with traditional methods, we would have had to create this top surface probably by doing a loft with multiple cross sections. So we can see using that wizard and using the regions makes that process quite a bit easier. I'm going to go ahead and hide my solid. Next thing I'd like to do is cut out this horseshoe-shaped feature. Again, we'll use the extrusion wizard. So I can pick the sides of that region, and then I'll pick the bottom. I'm not going to pick a top, but I am going to tell it I'd like to do a solid cut. So when we hit the next button, it's going to show me the preview of that extrusion where it extends beyond the top of our object. Once I hit check, it does that cut for me. And just like when we did the auto surfacing, we can also use our accuracy analyzer here and check how we're doing. So this tells us a couple of things right off the bat. One, most of it's green, so that's pretty good. This glaring red feature here, that shows me that, hey, I've missed something. I haven't put that pocket in yet. Same thing with the gray where the holes are. So using your accuracy analyzer, not only does it tell you how accurate your model is, but also kind of shows you what you have left to do on it. So let's do those holes next. Now I'm going to go ahead and do this the old-fashioned way, and we'll do that with a mesh sketch. So I picked that planar surface on my model, and if I offset that a little bit, you can see it gives me a nice cross-section through those holes. So when we use a mesh sketch, we get this pink outline here. That is a cross-section through your mesh, and we call that a reference polyline. And then we use our sketching tools to fit real geometry to those elements. So I'm just going to pick these circles here. Now, if I wanted to, I could go in and I could dimension these. All right. So it's 0.2931. So let's say, you know, as an engineer, I want to make that 0.3. You can also, in your sketches, add some constraints to your features. So if I select all these, I can make them all an equal radius, because that's probably how this part was designed, right? All those holes should be the same size, but in reality, they may not be. So now I've got my holes sketched out. Next step will be to do that extrude. Now again, I can take advantage of my regions, so I can extrude up to a region at the bottom of a hole, so we don't have to measure anything. And we're just going to extrude in the other direction to make sure we do a nice clean cut. If we turn our model back on, now we've got our holes cut in there. Looks like we've got about 2 more features we will need to do in this part. So we've got this kind of smiley face cutout. So I can actually create a mesh sketch directly from a planar region. I don't need to create a separate plane. We're going to offset that a little bit here. Let me hide my scan data. So here we cut a section using that region in this area. We want to do the smiley face. Now, when I did the holes, I manually picked circle. So we have all these sketch elements, or you can also do what's called an auto sketch. This is where you don't have to tell the system what type of entity you want to create. You just pick the reference polyline, and it decides what's the best fit for that segment. So here it's created all these radii, and it also puts a tangency constraint between them. So for some shapes, using the auto sketch may be a little bit quicker and easier than fitting those manually. And then finally, we'll do the extrude cut. And then we have that feature. All right, so we are just about done. Last thing we'll do is put a fillet up in this corner. Now, if I don't know what that radius is, we have this little magic wand tool. So if we click that, the system's going to interrogate the underlying scan data and recommend a radius to me. Let's go ahead and pick these edges as well. That probably propagates all the way through. And so now our model's complete. So that is how we create a parametric model. So if I did use the live transfer to send this over to SolidWorks, then all these features and all these sketches and everything else would be sent over and rebuilt in the native CAD system. If we just saved it as a step model and we imported that, then that would be what I call a feature-based model. Okay, so I'm just going to check here, see if we have any questions that came through. Okay, first one is using regions, does it build with symmetry or to the region surfaces? Okay, so when you use regions, it's actually fitting to the regions, so it is not inputting any kind of symmetry. So if you can, and I've done this before too, kind of use the regions and the wizard as a first guess, but then you can come back in here because it is parametric, right? I can come back in here and throw a center line in and maybe trim everything up. Oops. Right, keep only half and then mirror it. And so now because I edited the sketch and made it symmetrical about a center line, now I know my part is symmetrical. Okay. Next question. Oh, looks like we don't have any more questions. Okay, so what I'd like to do next is show you a real project that we did using some hybrid solid modeling. So let me go ahead and open that file up. So this one's actually going back quite a few years, but the techniques that we use really haven't changed much. So this is a medical instrument. Our customer needed a 3D solid model. So we can see it is quite a complex shape. So I'm going to go ahead and roll back in the history tree and point out a few things. Roll back here. So it looks like we scanned this part in a couple of different pieces and then edited those data sets together. The first part, the exterior housing, you can see we made a copy of the original, kind of smoothed things out a little bit and filled some holes, and then used this body to do some auto surfacing. So really good at capturing those organic shapes really quickly. And then since it's a watertight surface, of course, that gives us a solid. So then we can do some other operations, like we can cut on it, we can put holes and things of that nature. The next area of the part, moving a little bit forward, we did one of those boundary fits. So in this area here, we created a curve network, by hand. Let's see if we can find that mesh. Oh, this one. So the kind of the goldish mesh here, again, was extended, cleaned up a little bit, and then we created this curve network, and then used those boundary fit surfaces to create this segment of part. So then that was trimmed up with some other surfaces to create a solid. Now we can see adding that geometry in there. And then I believe the rest of the part was pretty much modeled, parametrically, where we added in, some cuts in here, cut the top off there, add some fillet radii. Just scroll forward here a little bit. Now this little knob section is pretty interesting because, as you can see, we use a few different cones to make the cutouts. Let's roll forward and see what that looks like. And we can see how that final knob came out with these crazy conical cutouts there. And we'll just kind of zip that to the end because I don't think there's too much overly interesting in some of the other pieces. But that is a very good example of where you would use hybrid modeling. Again, you've got geometric features, model those parametrically. You've got very organic freeform shapes here. So those are modeled with the different surfacing techniques. Combine all that to give us one final solid model. Well, that pretty much concludes our presentation for the morning. I'm going to go ahead and pull our PowerPoint up again. So I'm going to hang out here and see if we have any more questions come through. If anything comes up, if you guys have any more questions, you need more information, anybody interested in either DesignX or perhaps some scanning 3D modeling services, we do offer all that. Please feel free to email me, dan@neometricstech.com. Give me a call on the cell, 407-963-9964. Feel free to contact me anytime. So looks like we do not have any additional questions that have come up. So I'd like to take this moment to thank everybody for taking time out of their busy day to sit in on our webinar here. And again, if you do have any questions that come up, I'll sit on the line here for a couple more minutes. But again, feel free to contact me anytime. Thank you all very much. Thanks.